Hello students, hope you are doing well. Myself Shachi Tandon from Crack Chemistry. Today I am here with the class 11 topic. The name of the topic is Photoelectric Effect. This topic is included in your class 11 Chemistry NCERT book part 1. The name of the chapter is Structure of Atom. Students, this topic you have to study in your class 11, as well as you will get various questions based on this topic in your various competitive exams as well as class 11th exams. The questions will be in the form of numericals and application based questions, which you can solve only if the concept is clear to you. So students, in this video I have tried to explain this photoelectric effect in a very simple and interesting way, and I assure you that after watching this video you will be able to solve all questions based on photoelectric effect. So before starting, I request you to please subscribe my channel and like this video and share this video with your friends also. So now let's see what we will study today. So children, first of all, we will study what is photoelectric effect. After studying photoelectric effect, we will study some important observations which we observed during photoelectric effect. After that, we will study the explanation of photoelectric effect by Einstein using Planck's quantum theory. So now let's see all these topics one by one. So first of all, I'm going to explain what is photoelectric effect. Children, in 1887, H. Hertz performed a variety of number of interesting experiments he has performed. In these experiments, what he has done, I want to show you with the help of this diagram. So H. Hertz, what he did, he allowed the light of a suitable frequency. So I'm just writing here, he strikes the light of a suitable frequency on the surface of certain metals like potassium, rubidium, cesium, etc. And to his surprise, he found that electrons are ejected from the surface of the metal. These electrons were called as photoelectrons. These electrons were called as photoelectrons, and the effect was called as photoelectric effect. So, photoelectric effect. So Hertz performed a number of experiments of this type by taking different metals. So he came to a conclusion that when light of a suitable frequency only, children, this is a very important point, the light which is going to be struck on the surface of the metal must have a definite minimum value of frequency. We will study about this value later on in the same video. So during his experiment, he found some very important observations. So these observations I'm going to write here one by one. First observation, what he found, that the first observation number 1 was that the electrons are ejected from the metal surface as soon as the beam of light strikes the surface of metal. That is, there is no time lag between the striking of the beam of light and ejection of electrons. So I can write here, there is no time lag. There is no time gap. There is no time lag. No time lag between striking of beam of light of suitable frequency, between striking of beam of light of suitable frequency and ejection of electrons. So that was the first point which was observed during photoelectric effect. The point number 2 is that the number of electrons ejected is proportional to intensity or brightness of light. So I'm writing second point here, second observation here, number of electrons ejected. Number of electrons ejected are proportional to intensity or brightness of light. So, number of electrons ejected are proportional to intensity or brightness of light. So, number of electrons ejected are proportional to proportional to intensity or brightness of light. What does it mean? It means that more the intensity of light, more the brightness of light, the more will be number of photoelectrons will be ejected. So that was the point number 2. Now the third point, which is a very important point I want to mention here, for each metal, this is the point number 3, children. For each metal, there is a definite minimum value of frequency. For each metal, there is a definite minimum value of frequency. So I'm just writing here definite minimum value of frequency. Definite minimum value of frequency, which is called as threshold frequency. Which is called as threshold frequency. So for each metal, there is definite minimum value of frequency, which is called as threshold frequency, which is represented by the symbol u0. So for each metal, definite minimum value of frequency, which is called as threshold frequency, is required for the ejection of photoelectrons. Is required for the ejection of photoelectrons. And this minimum value of frequency, I already told you that it is called as threshold frequency. It is also called as work function. It is also called as binding energy. You will study in the same video. So always remember that if the value of frequency of incident radiation is lesser than u0, is lesser than threshold frequency, children, no electrons will be ejected. How long you are striking the metal surface with this beam of light, which is having frequency lesser than threshold frequency. Now, next point I want to discuss here, kinetic energy of ejected electrons. Children, this is the 4th point I want to discuss here. Kinetic energy of ejected electrons. Ejected electrons means I'm talking about photoelectrons. So, kinetic energy of ejected electrons is proportional to the frequency of light used. So, kinetic energy of ejected electrons is proportional, means it increases. Kinetic energy of ejected electrons increases with the increase of frequency of light used. Kinetic energy of ejected electrons increases with the increase of frequency of light used. Increase of frequency of light used. I hope all these 4 observations you have understood nicely. So, kinetic energy of ejected electrons increases with increase of frequency of light used. So, children, I just want to discuss these points quickly. So, kinetic energy of ejected electrons increases with the increase of frequency. So, I'm just writing here frequency used. So, what we have seen that quickly, I just want to revise this point. This observation was done by Hertz. What he observed that when light of a suitable frequency is allowed to strike on the surface of certain metals, electrons are ejected from the surface of metals. These electrons are called as photoelectrons, and this effect is called as photoelectric effect. And he observed that only certain metals, they show this effect. These metals are potassium, they may be rubidium, they may be cesium, etc. So cesium is Cs. So he observed some important observations during this effect. First observation I told you, the first observation is that there is no time lag between the striking of metal surface with the light of a suitable frequency and the ejection of electrons. Means as soon as the light of suitable frequency strikes the metal surface, electrons start ejecting. Then the second point I told you, number of ejected electrons are proportional to intensity or brightness of light. Point number third, for each metal there is a definite minimum value of frequency. This value is called as threshold frequency. It is also called as binding energy. It is also called as work function. W naught, which is represented by the symbol W naught. So for each metal, definite value of frequency is required, which is called as threshold frequency for the ejection of photoelectrons. If the value of frequency of the striking beam of light is lesser than this threshold frequency, children, always remember no photoelectrons will be emitted how long you are striking the surface of metal with a beam of light. Then point number fourth is that kinetic energy of ejected electrons increases with increase of frequency of light use. So children, I hope these points are very clear to you. Now all these points which I have discussed are written here. All these 4 points I explained with you. Now I just want to show you the effect of frequency of radiation on the kinetic energy of electrons, as well as effect of intensity of light used on the kinetic energy of ejected electrons graphically. So children, with this graph you can see that here you can see this is the nu naught. Nu naught is called as threshold frequency. Children, what is threshold frequency? As I told you, threshold frequency is the minimum frequency, is the minimum value of frequency which must be possessed by striking light for the ejection of photoelectrons. If the value of frequency of striking light is lesser than the nu naught, children, no electrons will be ejected. So you can see here this point represents the nu naught. After that, once we are increasing the frequency, you can see that the kinetic energy goes on increasing here. So the graph clearly indicates that the kinetic energy of ejected electrons increases with increase of frequency of incident radiations. Then please look at the second graph. Second graph is showing you the intensity of light, and we have plotted a graph between kinetic energy of ejected electrons versus intensity of light used. So you can see here it's very clear from the graph that there is no effect on the kinetic energy of ejected electrons with the intensity of light. We are getting a constant value. We are getting a parallel line. So I hope this point is clear to you. So I just want to write the points which I have discussed with you just now in the form of the statement. The first statement was that kinetic energy of ejected electrons. Ejected electrons means I'm talking about photoelectrons. So kinetic energy of ejected electrons increases. Kinetic energy of ejected electrons increases with the increase of frequency of striking light. So that point I discussed with you in very detail. I have shown you this point graphically also. So the point explains that kinetic energy of ejected electrons increases with the increase of frequency of the striking light. Then the second point was that let me write this point, increase of frequency of striking light. And the second point was that the kinetic energy of ejected electrons is independent of intensity or brightness of light use. So I'm just writing here kinetic energy of ejected electrons. Ejected electrons means I'm talking about photoelectrons. So kinetic energies of ejected electrons is independent of intensity or brightness. Independent of intensity or brightness of light used. Intensity of light used. So these are the two important points which we have seen with the help of the graph. Now one more point I want to mention here, children. All these observations could not be explained on the basis of classical law of physics. So all these points, whatever we have discussed here, could not be explained on the basis of classical law of physics according to classical law of physics. So I'm just writing here according to classical law of physics. According to classical law of physics, the energy content of beam of light depends. The energy content of beam of light. The energy content of beam of light The energy content of beam of light depends on the brightness of the light, intensity of the light. So the energy content of the beam of light depends on intensity of light, depends on brightness of light, depends on the brightness of light. So that was according to classical law of physics. So the points which we have discussed just now could not be explained on the basis of classical law of physics. Depends on the intensity or brightness of light. So now we have seen that, just now we have seen that number of electrons ejected, and according to this point, according to classical law of physics, what should happen? The number of ejected electrons and the kinetic energy associated with them should depend on the brightness of light. So I'm just writing here, according to classical law of physics, thus I'm just writing here, according to classical law of physics, the number of electrons ejected, the number of electrons ejected, and kinetic energies associated with them, and kinetic energies associated with them and kinetic energies associated with them should depend on the brightness of light. Should depend on brightness of light. But actually it didn't happen. Should depend on brightness of light, but we have seen during the observation of photoelectric effect, it doesn't happen. We have just now we have seen that number of electrons ejected depend on the brightness of light, but the kinetic energy of electron doesn't depend. Just now we have seen that it never happens. The number of ejected electrons depend on the intensity of light. Number of ejected electrons depend on the intensity of light used. Depend on the intensity of light used. Intensity of light used. So number of ejected electrons depend on the intensity of light used, but the kinetic energy of the ejected electron doesn't depend. So I'm just writing here, but the kinetic energies of ejected electrons doesn't depend on intensity of light. Doesn't depend on intensity of light used. So quickly I want to revise the point. Just now we have seen 4 observations, children. We have seen that kinetic energy of ejected electrons increases. Kinetic energies of the ejected electrons increases with the increase of frequency of striking light. And we have seen that kinetic energies of ejected electrons is independent of intensity of light used. So these 2 points couldn't be explained on the basis of classical law of physics. According to classical law of physics, the energy content of beam of light depends on the brightness of light. So What does it mean? If this point is correct, then the number of ejected electrons and the kinetic energy associated with them should depend on brightness of light. But we know it doesn't happen. Number of ejected electrons depend on the intensity of light used, but the kinetic energy of ejected electrons doesn't depend. I just want to show one example here. For example, yellow light. We are talking about the yellow light. The yellow light. This yellow light is having frequency in the range of 5.1 to 5.2 into 10 to the power 14. Frequency of yellow light is in the range of 5.1 to 5.2 into 10 to the power 14 per second. This light can cause the emission of electrons in the case from the surface of potassium metal. So yellow light having the frequency of 5.1 to 5.2 into 10 to the power 14 can emit electrons from the surface of potassium metal. So can emit electrons, from the surface of potassium metal, But if we take another light, suppose we are talking about the red light. But the red light of any brightness. What is the frequency of red light? I'm just writing here, red light of any brightness. Red light, the frequency of red light is in the range of nu is equal to 4.3 to 4.6 into 10 to the power 14 per second. So red light of whose frequency lies in the range of 4.3 to 4.6 into 10 to the power 14 per second of any brightness, of any intensity. So of any brightness may strike on the surface of potassium metal, but electrons will not be ejected. So any brightness may strike the surface of potassium metal for hours. May strike the surface of potassium metal for hours. But photoelectrons are not emitted. But ejection of photoelectrons doesn't take place, but photoelectrons are not ejected. So I hope that you must be getting an idea why it is happening this. You have seen that the frequency of both the colored lights you have seen. So just let me complete this line here. You have seen that just now. So what we have written here, of any brightness may strike the surface of potassium metal for hours. So you have seen that the yellow light is having frequency in the range of this. It can emit electrons from the surface of potassium metal. But what about red light? The frequency of red light is in the range of 4.3 to 4.6 into 10 to the power 14 per second. If this light strikes the surface of potassium metal for hours, the electrons will not at all be ejected. Doesn't matter how long you are striking this light of this particular frequency on the surface of potassium metal, and whatever is its brightness. So the reason is that, the frequency of yellow light is more, and the frequency more than the threshold frequency of potassium metal. So what is the threshold frequency of a potassium metal? Children, I'm just writing here the threshold frequency. Threshold frequency means nu naught for potassium metal is. I'm just writing here nu naught. Threshold frequency for potassium metal is 5.0 into 10 to the power 14 per second. 5.0 into 10 to the power 14 per second. I hope you must get an idea. Immediately you have seen that what is the reason? Electrons are electrons can be ejected using which light, which color light? Just now we have seen that electrons can be ejected by using a yellow light. But if we use the red colored light of any brightness for hours, the electrons are not at all ejected. The reason is very clear that nu naught, threshold frequency for potassium metal, is 5.0 into 10 to the power 14 per second. So therefore, yellow light has the frequency more than the threshold frequency of the potassium metal. That's why emission of electrons cannot take place. Children, I hope this point is very much clear to you. Now, I just want to discuss a point here. We will see the explanation of photoelectric effect using quantum theory. So, how this photoelectric effect can be explained by using Planck's quantum theory. We will discuss this, but I hope all these points are very much clear to you. We have seen that what is photoelectric effect, what are the observations which are used during photoelectric effect. After that, we have seen that by taking an example, the kinetic energy of ejected electrons depends on the frequency of incident light, but it doesn't depend on the intensity of light used. And one more point, we have seen that for every metal, for each and every metal, there is definite minimum value of frequency. For each and every metal, there is definite minimum value of frequency. There is definite minimum value of frequency. There is definite minimum value of frequency. This frequency is called as threshold frequency, which is called as threshold frequency. Threshold frequency is represented by the symbol nu naught. So for every metal, there is a definite minimum value of frequency called as threshold frequency is required for the ejection of photoelectrons. And if the value of frequency possessed by the striking light is lesser than the threshold frequency, no electrons will be ejected. How long you are striking the metal surface with the light of that lesser frequency, electrons will not at all be ejected. And one more point I want to tell you here, that this threshold frequency is also called as, I have written here threshold frequency. This threshold frequency is also called as work function. I'm just writing here work function, which is represented by the symbol W naught. All of them have the same meaning, and it is also called as binding energy. We will discuss all these points just now. So now we are going to explain the photoelectric effect using the Planck's quantum theory. So explanation of photoelectric effect was given by Einstein using the Planck's quantum theory. So children, I just want to draw a simple diagram for explaining the photoelectric effect. This is the surface of the metal. In the surface of the metal, this one is an electron shown here, and we are using the light of a suitable frequency. So this is the incident light of a suitable frequency. So I'm just writing here, this is the incident light. And children, this incident light must possess a definite minimum value of frequency for the ejection of photoelectrons. So now what will happen? The incident light is made up of photons. Children, this is in the Planck's quantum theory. I'll give you some brief information here, but the detailed description you can find in my video, Planck's quantum theory. So what will happen? The incident light, the light is made up of particles which are called as photons. So incident light is allowed to strike the surface of the metal. A portion of its energy is used for what? A portion of its energy is used to remove electron from the metal surface. This energy is called as binding energy. So I'm just writing here, this energy is called as binding energy. I'm talking about this much energy is required here. It is also called as work function. I mentioned in my previous slide about the work function, which is represented by the symbol W naught. So W naught is called as work function. So work function, basically it is energy. And what is the value of this energy? The energy is equal to h nu naught. This value was given by Planck in his Planck's quantum theory. What is the Planck's quantum theory? This point in brief I want to explain here. According to Planck's quantum theory, the radiations are made up of small particles which are called as quantum. And in the case of light, these particles are called as photons. And the energy associated with each photon, according to Planck's quantum theory, energy associated with each photon is equal to h nu. So now I'm just coming back to my topic. When the light of a suitable frequency strikes the surface of metal, you can see that a portion of energy of this photon is used for removing electrons from the surface of metal. So this energy is called as work function, or you can also call it as binding energy. You can also call it as binding energy, or you can also call it as the threshold energy, or you can also call it as threshold energy. So now I just want to explain the point here, whatever I have discussed. When a beam of light of suitable frequency strikes the surface metal, a portion of its energy is used for removal of electrons. This energy is equal to the binding energy of the metal, and the remaining energy is imparted to. Remaining energy is given to ejected electron. So I'm just writing electron here using a different color pen so that it will be easy for you to find it out. So energy of the ejected electron, remaining energy of the photon is given to the ejected electrons, and that energy will be equal to half mv square. So what will be the value of that half mv square? I'm just going to discuss with you. So children, I'm just coming back to this point. I'm just writing here this half mv square will be equal to h nu minus h nu naught. How this value is will come, I'm going to derive just now. So I'm just writing this in a red color box so that we can come back to this point after doing the derivation. So what I was discussing here, when a light of a suitable frequency strikes on the surface of metal, what will happen? A portion of the energy of the photon. I'm repeating my point. The beam of light is made up of small particles which are called as photon. Each photon possesses energy which is represented by the equation E is equal to h nu. So when a beam of light strikes the surface of metal, the photon transfers. A part of energy of photon is used for removal of electron from the metal. This energy is called as binding energy. It is also called as work function. It is also called as threshold energy. And what will happen to the remaining energy? The remaining energy is given to ejected electrons in the form of kinetic energy. So I'm just going to derive a relationship for this. We can write here energy of a striking photon. Energy of striking photon. Are you able to try the answer where it is used? It is used, a part is used as in the form of binding energy. I told you it is used to remove electrons from the metal. It is represented by the system X. It is also called as work function plus half mv square. Half mv square means the remaining energy of the photon is given to ejected electrons in the form of kinetic energy. So what is X here? X is the threshold energy. So I am just writing here, children, X is threshold energy. X is threshold energy. What is the value of threshold energy? threshold energy is equal to h nu naught. What is nu naught here? Nu naught is threshold frequency. So I can substitute these values here in this equation number 1. I am giving this equation to the equation number 1. So energy of a striking photon will be equal to h nu. And what will be the value of x here? X will be equal to h nu naught plus half mv square. So with the help of this equation, we can find out half mv square. Children, what is half mv square? Half mv square is the kinetic energy of the electrons. So I can write here half mv square is the kinetic energy of electrons. So kinetic energy, which is equal to half mv square, will be equal to h nu minus h nu naught, or we can write here kinetic energy will be equal to h nu minus nu naught. So children, I hope these points are very much clear to you. So we have derived this equation just now. We have seen that kinetic energy of the ejected electrons will be given by this equation kinetic energy. Kinetic energy is equal to half mv square. That kinetic energy will be equal to h nu minus nu naught. Children, I hope this point is clear to you. Now I just want to show you the previous slide where in this diagram I have written the same equation. I told you, okay, I'll come back to this slide once I derive this. So we have got the relationship here, half mv square is equal to h nu minus h nu naught. So children, I hope this point is clear to you. So this explanation was given by Einstein by using the Planck's quantum theory. So Einstein explained this photoelectric effect, explained the photoelectric effect using Planck's quantum theory. Effect using Planck's quantum theory. So as I already told you that Planck's quantum theory I didn't discuss with you in detail. For knowing about the Planck's quantum theory, you can refer my video on the Planck's quantum theory. So, but in brief, I told you about the Planck's quantum theory. According to Planck's quantum theory, energy is not radiated, not emitted continuously, but in the form of small packets, and these packets are called as quantum. They are called as quanta, and the singular will be quantum. And in the case of light, these packets are called as photons. Photons, they are called as in case of light. So now I told you that the energy associated with each quantum will be given by the relationship E is equal to, actually E is directly proportional to nu. The energy is directly proportional to frequency of radiation, and E is equal to h into nu, where h is a constant which is called as Planck's constant. So children, you have to memorize the value of the Planck's constant also. What is the value of Planck's constant? I'll write here. The value of Planck's constant is 6.626 into 10 to the power minus 34 joule into second. So this is the value of Planck's constant. Now, the above equation which we have got just now can explain the experimental facts as discussed below. So I'm going to discuss the experimental facts on the basis of the above equation. Above equation means I'm talking about the equation which we have received just now. Half mv square. What was half mv square here, children? Half mv square represents the kinetic energy of the ejected electrons. So half mv square, that will be equal to h nu minus nu naught. So you can see that all the facts regarding the photoelectric effect can be explained so nicely by using this equation. So children, please look at the equation. From this equation, it is very, very clear that if the frequency of radiation nu is less than nu naught. So if frequency of radiation nu is less than nu naught, are you understanding my point? I'm talking about if the frequency of the incident light is lesser than threshold frequency, lesser than nu naught, no electrons will be ejected. So I'm writing here, no electrons will be ejected. No electrons will be ejected. How long the beam of light strikes the surface of metal, or whatever the intensity of the beam of light is, though and remember that threshold frequency is different for different metals. This point also you have to remember. So I just want to repeat the first point again, children. If the frequency of incident beam of light is nu, is lesser than threshold frequency of the metal, no electrons will be ejected. How long? It doesn't depend how long the beam of light strikes the surface of metal, or whatever the intensity of incident radiation is, and threshold frequency nu naught is different for different metals. This point also I have already mentioned. Nu naught is different for different metals. So I hope this point is clear to you. Now I want to discuss the second point using the above equation. So what is the second point? Second point is that if the frequency of striking radiation, that was nu, is more than nu naught. What is nu naught? Nu naught is the threshold frequency. So if the frequency of striking radiation, nu is the frequency of striking radiation, nu naught is the threshold frequency of the metal. So if nu is greater than nu naught, then the photoelectrons will be ejected. You can see that energy of the incident radiation is more. So what will happen to the excess energy? The excess energy. What is the value of excess energy? The excess energy is h nu minus h nu naught. So excess energy is h nu minus h nu naught, will be imparted to ejected electrons in the form of kinetic energy. So I'm just writing here will be, I'm using the next slide, will be imparted to ejected electrons, will be imparted to ejected electrons in the form of kinetic energy. I hope this point is also clear to you, children. Then third point is that since each photon, I'm just going to explain the third point here, each photon can eject the electron. 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 So on increasing the intensity of light of a given frequency, on increasing the intensity means brightness, on increasing the intensity of light of a given frequency, on increasing the intensity of light of a given frequency, what will happen? Are you getting any idea? On increasing the intensity of light of given frequency, what will happen? The number of photons striking the surface increases. Number of photons striking the metal surface increases. Number of photons striking the metal surface increases. So what will happen? Are you getting the answer? Once you increase the intensity of the incident radiation of any given frequency, the number of electrons will increase. And as each photon can eject the electron, what will happen? The number of photoelectrons emitted will increase. This will result in the ejection of more photoelectrons. I'm just writing here, more photoelectrons will be ejected. More photoelectrons will be ejected. So I hope all these points are very clear to you. I try to explain you in a very interesting and simple way. Children, In case if you have any doubt, please write your doubts in your comment box so that I can clarify your doubts. I hope all these points are clear to you. So children, let's see what we have discussed today. We have studied about photoelectric effect. That was the first point. After that, we have seen what are the important observations during photoelectric effect. 4 observations we have discussed. After that, in brief, we have studied about the Planck's quantum theory also. Then we have done the explanation of photoelectric effect by Einstein using Planck's quantum theory. So the topic was very interesting topic, and I hope that you understood this topic nicely. Please watch this video again and again so that the concept will become very clear to you. And in case of any doubt, please post your doubts in the comment box so that I can clarify. In the end, I want to say thank you so much for watching my video. Please like this video, share this video with your friends and subscribe my channel. Don't forget to watch my next video. Thank you so much. Have a nice day.